So this maybe relates to your group presentation type things. We'll talk about it. Just enjoy the calm before we get rolling. Oh, it's magic. Kind of fluid mechanics, I guess thermodynamics as well, right? Tricks you can take out with you on Thirsty Thursday. No doubt. Yeah, interesting stuff. All nucleation sites, right? That's kind of the deal going on there, I think. Not so interesting, this, I don't think. You know that, so. We'll talk about fluids today, in introducing them. What else we got going? Why not? Come early, the front seats are filling up fast. There you go. I guess you start seeing a theme, right? Water in different states, liquid and solid. From a couple of days ago.
First we thought that it was whale poop, but then it became obvious that there was way more of it than any normal sized pod of whales could come up with.
Apparently the size of Manhattan.
When it got to quite thick, there was no water. It was just a field to the horizon on all sides. The noise on the video does not really justice. It's like an mixer.
Do any of you ever use pumice?
Grinding.
You can buy it to braid skin off you in the bath. Volcanic rock that's full of air.
Noise stops, and we can hear the water again.
It's coming from a submarine volcano. A volcano that is about 130 meters below sea level. And this volcano erupted more less suddenly, probably, and created lots of rocky volcanic rocks that are buoyant, and those rocks burst.
So you get the picture. So we'll see if that comes through on the recording. So lots of things are copyrighted, and especially BBC things. I get these copyright infringement notices, and they never take them down. But
since the unthinkable happened, it took just seconds for the dam to collapse. A torrent of toxic sludge engulfed everything, everyone in its path.
So this was this summer, right? Early this year.
Many in the mine's staff canteen. They just sat down to lunch.
So yeah, this is a valet mining operation. This is a tailings dam. So you mine the ore, you process it, you have all this sludge left over, and you put the sludge, you make a dam out of the sludge and you impound behind it, and you leave it there, hopefully stably, but not always stably. And so this was a collapse that occurred, I think early this year in Brazil. Put all of their mining operations kind of under extra scrutiny, killed 300 people, I think, as well. So fluid mechanics, obviously. Fluids acting on a dam to destroy it. We'll talk about that in the next couple of weeks. Not in this particular context, but in general. And the other thing, I guess, it reinforces is, as an engineer, as many of you will be, the responsibility that we all have to look after the public good, to look after the public welfare. And so one of the reasons that you want to know fluid mechanics is that you don't end up making mistakes that will harm people and get you in court. And so that's just one maybe sobering message to come out to all of us in terms of the responsibility we have to society. Okay? So that's the precursor to what we will talk about today to get things rolling. I guess last time I couldn't quite get Canvas to open, so I made sure it would open before. So let's just do some housekeeping things before we get going with material proper. I know I'm missing something out on the left-hand side. I guess I can put this in student view, which is what you would see. There should be announcements that you've had already in terms of deliverables. The two things that are worthwhile noting are that each week there'll be announcements to tell you what's due the next week. But in terms of the assignments, there are two things behind the firewall, quote unquote, that I mentioned that it might be worthwhile getting hold of. The first is the homework problems, which I said are from the 7th edition of Munson. So you can download those to your desktop and use them. We looked at them last time. It's just a PDF file that includes the 13 homework assignments questions. And the other thing, so many of you have come in since I asked this question, whether you downloaded the midterms and final exams from previous. If you haven't, you should, just because those, as I mentioned before, 75% of the grade is on the midterms and the final, and so the questions that are there are certainly representative of what you'll see in the future. And so it wouldn't be a bad idea to take the first midterm, of which there are versions of that back to 2009, I guess 10 versions total, and be able to look at those and to see how comfortable you feel with them. I know we haven't really started yet, but the examples are worked, so you can actually get a feel for how comfortable you are with the material. It might be a blow-off class where you understand everything because you've seen it in physics at high school and physics classes here, or it might not be. And so you can calibrate maybe the time that you want to spend on it based on that. There is no homework until the homeworks are due every Thursday at midnight. And so the assignments, as I mentioned, are defined in that downloadable sheet. They're from Munson 7th edition. The submission, though, is online. And so the submissions are just a way to be able to the questions aren't there, but the questions are in the PDF, and so you just need to go through and answer them appropriately to what they might be. Whoops. There should be, however many there are for each question. So I don't know how many there are here, but you should be able, if there are 5, you should be able to get 20% of them right just by guessing, right? Just on, if there are 5 parts. You get 3 attempts. It tells you after the attempt what was incorrect or correct. And so you can go back and so you can actually, if you had 5 attempts, probably you could game it yourself. If you have 3 attempts, probably you can game it with your colleagues. I don't know whether there are solutions floating around. I can't imagine there aren't solutions floating around, but that's not the point. And so you need these as practice to feel comfortable with what you're doing. So it's on the honor system to do that. But anyway, so you see the way of doing it. So you have 3 attempts. I think on this first one, probably you have 5, and it probably shuts off on Friday instead of on Thursday at midnight. Just self-preservation for me, so I don't have to answer, can you reset it 100 times? So that's as a courtesy to you. So that's the mechanism of submission for your assignments. The other thing, I guess, is that there are quizzes. The first quiz, which is optional, is for Labor Day, Monday. And so, it's not open yet. So it'll open on the 30th. Today's the 28th, right? It'll open on Friday. And so you'll see exactly what that is, and we'll mention it. But Labor Day is usually on it's the first Monday of September, right? Happens very early this year, about as early as it can be. Maybe it's the 2nd of September this year. And so usually this holiday is at the end of the 2nd week, but it's not. So it switches. Anyway, so you have an assignment to do. So the quizzes are optional. You need the material, but so you're probably better off doing it. They are due 2 classes later. So this will close, a Monday quiz will close on Friday at midnight. A Tuesday quiz will close on Monday at midnight. And a Wednesday quiz will close on Wednesday at midnight, I guess, right? So you get two sessions to be able to do it. Okay? So that's kind of the last of the bookkeeping stuff that perhaps we need to take care of. Okay. So, any questions come from that before we get rolling? Is the lighting just perfect? Go ahead.
So the optional quizzes aren't graded at all?
They are graded. They're graded. The optional quizzes, optional, are worth 7% extra on your grade.
Oh, okay.
That's the 7% extra. The new syllabus is up, in which that 7% is right here, by the way. And it also has on it Zach's office hours. So Monday, Wednesday, 10:30 to noon 30, and Tuesday, Thursday, 10:30 to 1:30. So not bad, all ahead of Thursday midnight, so the timing is fine for you to get some help with your homework, if you so need it. But again, don't rely, if you're acing the homeworks, no problem, do look at the exams, because the exams are what count for the 75% of this grade. Not quite 75, because as we said last time, the total grade is really out of 114.5 when you add the 10% extra for each exam and the 7% here for these optional quizzes. Okay? Optional because it's above and beyond the grade system. Okay? Any others? Questions? AGL. All right. Well, let's get rolling. I should be mindful, I guess, of the fact that some of this disappears off to the side. So every day, the stuff that you can download from the course resources page. One other thing. While I do it, why don't I do this? The one other thing that's on here, I added to the course resources page, is some previous student group presentations. And so you can look at these if you want. I like this one, not necessarily because of the content, just for the way that the guys presented it.
So we're going to be doing how does the state of a Formula 1 car allow it to grip to the surface it's driving on?
And so, nice way to present it. So I think you can see by looking at them, you get some appreciation of the range of topics that people have taken. I've chosen to put the best ones up. So these are all ones that were top scoring in the rubric, and so you can get some appreciation of that when the time comes. We'll make groups after Wednesday in week 3, after all people have added and dropped the class, and the class enrollment has stabilized somewhat. So I thought that was interesting. So you can go back to that, and you can see exactly what other people have done in the past. So right here. Okay. So what we'll do each time, so week 1, class 2 is where we are now. And so we'll forge ahead and talk first about fluid properties. In terms of big picture, if you like, where we are in the class, the first couple of weeks we'll spend talking about fluid statics, properties of fluids and fluid statics. We'll talk about pressures on structures, like dams, for instance, that might want to fail. These are all for static fluids, fluids in a beaker, if you like, that could be accelerating but aren't circulating. We'll talk about moving fluids, inviscid fluids, through Bernoulli equations for a couple of weeks. We'll spend 3 weeks talking about control volumes, conservation of mass, mass in equals mass out, conservation of momentum, which is Newton's second law, F equals ma, and conservation of energy, which allows fluids to impart energy to wind turbines and generators, etc. And then we'll talk about applications. Similitude, for using scaled models, like the Poseidon adventure, for instance, to say something about fluid mechanics. Flow in pipes and pipe circuits, which is kind of a recipe for pumping fluids up from wells or around plants. External flows, such as over airfoils and wind turbine blades, for example. And then open channel flows. Really, there's only 13 weeks, not 14. The last one is just a single week. So that's kind of our way through the material. So the first topic is to really talk about fluid properties, and that's what we'll start talking about today. Just to maybe reinforce the idea that fluids are everywhere, you can think of fluids in a bunch of different systems. I know that's off the edge. That probably isn't. And so here are just some examples. The planet we live on is fluid beneath the crust, solid crust, and relies on circulation that creates new plates at boundaries, constructive boundaries, and creates earthquakes and destroys plates at destructive boundaries. So it is a fluid mechanics system, albeit a very viscous system. Hurricane, it's not Damien, it's Dorian, Hurricane Dorian, now bearing down on Puerto Rico 2 years after Maria, is clearly a fluid mechanics system in the atmosphere with impacts on the sea underneath it, which is liquid and gaseous form. Tsunami, which come from earthquakes, which we know from the Boxing Day tsunami of December the 26th, 2004, when you'd have been quite young, in Indonesia, which killed 200,000 people, is exactly because of this displacement on the seabed, which all of a sudden creates a step in the water, which has to ameliorate by flowing. Deepwater Horizon, circulation of oil within the Gulf of Mexico. Greenland, last time I checked, it still belonged to Denmark, but ice sheets on that are flowing. And ice, actually, as we saw earlier, creaks and flows at a glacial pace, as someone would say. And too early for you, 1980, the eruption of Mount St. Helens in Washington State, which was a lateral blast, which killed 60 people, but other than that, and damaged air traffic and the infrastructure, I guess, in the northwest for the summer of that year is also pressurization from fluids that break open the carapace. In engineered systems, we rely on fluid mechanics in lots of things we do. If you take a plane, you rely on lift from an airfoil. Deepwater Horizon is fluids going up pipes, sometimes not going up in the drill stem or in the casing. The gas actually from the reservoir went outside the casing, between the rock and the casing, and came up onto the rig and actually destroyed the rig ultimately. The rig collapsed and also ended up jettisoning millions of barrels of oil onto the seabed. When you take a plane, even though GPS will tell you where you are, plane speed is often defined by pitot tubes. You'll see them if you get onto a commuter plane in State College. and it just relies on the plane forcing its way through the air pressure against it, momentum of the air causing a pressure change, and that pressure reading gives you is correlated with the velocity of the plane. Correlated with the tragic loss, I guess, of Air France. I don't know what the flight number was. Rio to Paris, disappeared off radar in a storm. The culprit was that ice froze this opening here, and it wasn't working. They didn't know whether they're going sub or super stall speeds, and the black box recorder, when they found it a year later or so, showed that they'd gone through a bunch of iterations, not knowing what the airspeed was, and they'd ultimately crashed in the deep Atlantic offshore of Brazil. Internal combustion engines is a fluid device. Every time you turn your heat on or your stove on in the morning, you're getting gas that is shipped up from the Gulf of Mexico through a huge pipeline system to the northeast, stored in caverns in Pennsylvania and Ohio, salt caverns, so it's there close to market for when everyone in New York City turns on their gas. Shale gas revolution, horizontal drilling, hydraulic fracturing as mechanisms that has completely changed the energy picture in this country in the last decade to be basically North America energy self-sufficient. Single axis, vertical axis wind turbines to generate electricity. Articulated floats for generating power from wave energy. So a force times a displacement, even if it's an angular displacement of these articulated joints, can be used to generate power, does work, force times displacement. Contaminated fluids dropping in the subsurface and being carried away as dissolved plumes and then being cycled into people's drinking water. Hot, dry rock, geothermal energy, the salvation of this planet, I think, possibly in terms of some renewable energy. Tacoma Narrows Bridge, must have seen it in high school. Fluid mechanics problem. Constant velocity wind creates kind of a von Karman vortex street on the downstream side. This vortex sheds a vortex below it and above the deck on each stage and puts it into some kind of oscillation. And if the oscillation is reinforced, it's at the right resonant frequency of the bridge to the forcing frequency of the wind, then the bridge ultimately destroys itself. In recreation, well, the Olympics, when Ian Thorpe, before your time, but certainly Michael Phelps, your time, was swimming. One Olympics, they had shark suits that they swam in because they would lessen fluid resistance by having a particular surface characteristic that would lessen drag. They only occurred for one Olympics, then they were gone. If you look at the Olympic pools that you have, I think they're something like 10 feet deep, not just 6 feet like a regular pool, so that they lessen drag on swimmers, so you can get the fastest times in Olympic, real Olympic 50-meter pools. The America's Cup, before it became a catamaran race, New Zealand beat the United States for one of the first times, maybe 20 or 30 years ago now. They always used to put the boats in the water with a shroud around the keel to hide the secret weapon in terms of providing stability to the boat and reducing drag. Wind transport, sails are not really just a placard that you blow against and gets pushed, but they actually are really airfoils as well. No doubt for our presentations, some of you will want to say why a baseball spins and curves as you put spin on it, why a golf ball has dimples on it, because it goes further, because it breaks down the boundary layer. Kayaking, kind of just like snowboarding, a balance, I guess, between gravity pushing downwards and frictional forces on the bottom of a snowboard, or fluid drag on the base of a kayak, which is why you can surf waves on rivers and stay apparently in the one spot. The water's coming down, it causes a wave. You sit on the face of that wave going downhill, and the water's flowing past you, pushing you uphill, and at some balance point you can just sit on that wave. And of course, throwing a football and twisting it to make sure it goes in the right place. So that's why you should be enthusiastic, hopefully, about this class. And so that's where we'll kind of start off, I guess, from here. So today, what we'll try and do in the time that we have left is talk about some of these different components: fluids versus liquids, dimensional homogeneity, and fluid properties. So let's, as I'm wont to do on occasions, let's flip back. Let me do, if I can do this and do this, because I can. So hopefully you can see both sides of that, I think, right? So let's see if I can do this. So this is one. So anyway, you'll get some feel of exactly what we're attempting to do. So if we look at fluids, solids, and liquids, maybe I can do this. Oops, not very good. Don't want that. So I'm just getting used to using this again. Of course, I've already slipped up. This should be liquid. I could have just got rid of it. But the essential components, I perhaps don't have to belabor this point, are that if you look at these, then clearly a solid is something that if you apply a force to it, it deforms, but it springs back to its original position. A fluid is something that uniquely can get a free surface with it. And a gas is something that will fill a container to completely fill it to its full extent. If we look at the characteristics of these in terms of properties that we have, there are probably a few essential properties that we can think of that define these. One is density. It's equal to mass divided by volume. And in our metric system, and we'll only use SI in this class, the book is in SI and English or imperial units, but we'll tend to use SI units only. So the unit in the SI system is a kilogram, and the length unit is a meter. And so if we look at those properties in terms of, let's see if I can do this. Why not? If you look at the density of a solid is quite high. The density of fluids are typically high to medium, I guess, and gas has a low density. If we look at viscosity, so this is how much it's like honey, I suppose. High viscosity honey, low viscosity water. Viscosity is defined in terms of Newton's law of viscosity, which we'll talk about in this first two sessions. And its term is mu. So mu is the viscosity. And so the units of viscosity are in SI units, newtons per meters squared times seconds, or sometimes referred to as Pascal seconds. So a Newton per meter squared is a Pascal multiplied by seconds. And in terms of that, again, solids have very high viscosity. Think of ice. That's a flowing solid, if you like. Water has a mid viscosity, and gases typically have very low viscosities. A third property that we'll use in this class and introduce in the first couple of sessions is also modulus. We will use the term E bulk, I think, and by definition, modulus is equal to the change in volume over the initial volume that occurs due to a change in pressure with a minus sign attached to it. And this seems like a blunt instrument more than I want. And so the units of this, since volume over volume have to be unitless, and pressure is the only remaining component, then this also is in newtons per meter squared, which is the same as a Pascal. And again, if we look at what that behavior is in terms of these individual components, solids have a very high modulus. Actually, fluids, if they're constrained, they also have quite a high modulus as well. Maybe we can think of it, if you look at water, it has almost the same modulus as rocks, maybe only a fifth as large, but quite high. And gases have a very low modulus. They're very compressible. So you could imagine taking a bicycle pump, for instance, and putting your finger over the top, compressing it. You know with air it will compress. But if you filled that bicycle pump up with water and try to do the same, it wouldn't compress. And so the modulus is that. And we'll also use the term compressibility. Which is just equal to 1 over modulus, which has to be 1 over pascals in terms of the units. So those define some of the component units that we'll use, the most important ones. So density, you saw the floating field of pumice. The density of that pumice is much less than water. That's why it sits on the surface. It's controlled by that. The others we haven't really explored yet. But actually, when you look at the wave, the velocity at which the wave traveled when that sheet, the ice cliff collapsed, will show that the velocity at which that flows is a function of some of these characteristic dimensions, actually mainly of density. Okay. We should talk also about dimensional homogeneity. People can read that, right? And so with everything, you need to add apples to apples and oranges to oranges. And so maybe the easiest way to describe this is to think about something like the definition of area, how we define area. So if you think of a coordinate system and you have something that looks like this. Whoops. So this is x1, x2. This is y1, y2. And you want to define the area of this. Then by definition, it looks like something like this. Right? And it would have limits. We know that the units of this have to be in length times length, which is the same as in our system, meters squared. So you could integrate this, and if you integrate that, you get this being equal to x, and substituting the limits, x2 minus x1 times y2 minus y1, right? And so you can see immediately that the units of this are exactly what they should be, is that they're in units of meters squared. And so what you could do is you could also see that when it's in its differential form, if you get rid of the differential operators, d and these integral operators, then the units you have still are x and y, and it should define the fact that the units of this should be meters squared. So the units that you end up with should absolutely be the right units for what you are projecting. If you're a petroleum engineering student, then you'll realize that lots of the equations that you use in petroleum engineering, you have to define the units. They're specific to the units that you use. That is almost never the case in this class. The units are defined in terms of their basic components, and you don't have to supply pressures in pounds per square inch and lengths in inches. If you use meters instead, then you get the wrong result if you plug it into those equations. So in this class, all of the equations we use, with maybe one or two exceptions, will all be dimensionally homogeneous in terms of what we're doing. Much of this class revolves around the adage from dynamics, which is Newton's second law. Force equals mass times acceleration. We could also write that as a change in velocity with time. Acceleration is change in velocity with time. And so, for instance, if you wanted to, you could be able to figure out exactly what the units of force are if you know the units of velocity, length over time, if you know the units of time, seconds, and if you know the units of mass, which are kilograms. And so if we did that, we'd know that this is equal to kilograms meters per second, meters per second times divided by time. So kilogram meters per second squared. And so, of course, this by definition is the definition of 1 Newton, right? 1 kilogram meter per second. The force required to give 1 kilogram an acceleration of 1 meter per second squared is a Newton by definition. And so the units of this are homogeneous. The utility in mentioning that is that one of the very first expressions we'll deal with is Bernoulli. And so Bernoulli relies on some kind of coordinate system where we have an elevation that we'll call z, vertically upwards, and a coordinate system. But more importantly, it'll define a coordinate system which is along a streamline and a velocity of flow within that streamline, which we'll call v. And so you'll know almost certainly from your physics on campus and also from your high school physics that we can write Bernoulli's equation as an elevation plus a fluid pressure term plus a inertial term, and that anywhere along a streamline that should be constant. The other thing that's worthwhile noting is that if you look at this relationship, then this is essentially equal to, I guess we could write this as a minus sign, I guess, instead of a 0, is that this corresponds to Newton's second law. This term represents inertia, overcoming inertia by accelerating something. The fluid, if it changes velocity as it goes from location to location, it has to be accelerating. And so it invokes this inertial term. And the other things are forces. They're related to the force that's applied by it being up at some elevation and the fluid pressure that's being applied by it having some static head attached to it. And so in the context of what we're talking about now, the units of this are what? The easiest one to figure is this. It has to be units of length. And for us, it has to be meters. So that means that these other two terms also have to be in the same units because we're adding apples to apples, and therefore that has to be the case. There are a couple of interesting expressions, I guess, that come out of this. One is that since these are all in units of length, we could divide each of these terms by each other and combine them in some way. And so if we do that for maybe these first two terms, say we divide this term by this term, right? This is length and this is length. So when you divide length by length, it should be unitless. So if we do that, then we end up with what? P over unit weight. I guess I should have mentioned that unit weight is equal to the product of density and gravitational acceleration. Density we've already defined. So this is rho g. And we're going to divide it through by v squared over 2g. If we do that, we can get rid of this. We can get rid of this. We don't really care about the 2 just because it's a multiplication factor. So we could define a term which is equal to pressure divided by density and the flow velocity squared. And we won't use that today, but we'll call that the Euler number, which is a non-dimensional number. Has to be because it's meters over meters. And it defines, for instance, the pressure that you apply against your chest if a jet of air is blowing on your chest at a velocity of v squared and goes from that velocity here to 0 velocity when it hits your chest. It's the force that's applied on a structure. So it's a very important term that we'll ultimately use. If we take, for instance, the other 2 terms, so this term here and this, and we look at the ratio of those. And so what do I want to do? I guess I want to do, if we take v squared over 2g, this term here, and we divide it through by z, then we end up doing the same manipulation we did before. Don't care about the 2, but we end up with v squared over gz, or we could also write that as v over square root gz. And this is called the Froude number. And it defines the velocity of a wave that travels in a fluid of depth z and on a planet where gravity acts at some particular value. So not things we'll use today, but things we'll use on Friday to understand the rate at which, for instance, a tsunami wave travels, which actually turns out to be very fast, as fast as a plane. Okay? So we always want to look for what we'll call dimensional homogeneity. You'll see that sometimes we use the notes, sometimes we jump backwards and forwards and doing different things. Well, we've done this, we've done this, we've done this. This is worth going to. This is from Munson. By the way, Munson is in the bookstore right now. If you want to get it, it was there on Monday. There was also a line, I counted it, there was 120 people in line for books on Monday, but they did split into 5 tills at the end or something. So if we're enforcing dimensional homogeneity, there are actually 2 systems that we can use. One system is to use mass, length, and time. So for us, that would be kilograms, meters, and seconds. And actually, there's another one. Where is it? Temperature is in here somewhere. We won't use it very much, but theta is temperature. So this would be degrees Kelvin, I suppose. Or there's also force, length, and time. In all the stuff we do in this class, I choose to use mass, length, and time just because I find it more intuitive. Because it breaks into the components which are the basic of the SI system. Kilograms, meters per second, and as a function of temperature. Okay? And so everything that we want to do, we can define in those terms. Most things are obvious. Area is in units of length squared. Some things aren't so obvious. But for instance, if you wanted to define exactly what stress would be, it's not so obvious that it's equal to mass, length, time minus 2. unless you think of a Newton as being a kilogram meter per second squared, which is mass divided by 1 over area, which is equal, probably going off the screen, right? Kilogram 1 over second squared meter, which is exactly this, right? Kilogram divided by length times squared. So you can always define exactly what it is. So you can do it that way, or alternatively, if you wanted to, you could realize that force is equal to mass times acceleration. Force divided by area is equal to stress. And so this is the same as the stress we defined before. So if you know what mass is, you know what acceleration is, and you know what area is in terms of units, you can always calculate exactly what the units are. And so we can always define exactly what those are. Okay? So let me switch back to this. Okay. So we've talked about the units that we might use. The other thing that we might think about is in terms of defining pressures and temperatures. And in terms of that, if we talk first about pressure, and I'm really talking about the scales on which we define it. So if we talk about pressure, there is an absolute scale and a gauge scale. So absolute pressure in a total vacuum is 0 pascals. Where we sit right now in this room is at 1 bar, 1 barometric pressure, which is the same as about 101.3, I think, kilopascals. And so 101 kilopascals is about the same as 0.1 megapascals. So kilo is 10 to the 3, mega is 10 to the 6. Certainly you have that in your background. But in gauge pressure, when you use a pressure transducer, it will probably tell you now, if you take the pressure here, it's actually 0 in terms of gauge pressure. And so in gauge pressure, it's at 0 kPa. And this would be minus 101 kPa. And as you increase, so these are just offset by 101 kPa. So that's important. And it's just because the fact that we take as reference the pressure that we live in at sea level, which is something like 101 kPa. And that's important when we talk about the ideal gas law. That's the main reason that we're talking about it. So that's pressure. If we look at temperature, then the same kind of applies. Absolute and, non-absolute, regular temperature. And so absolute 0 in absolute pressure is 0 Kelvin, after Lord Kelvin. And that means that the temperature we're at right now, is 273 Kelvin plus probably 20 degrees, but 0 centigrade is 273 Kelvin, which is the same as 0 degrees centigrade. And so this is minus 273 Kelvin. And of course, the temperature we're at right now, room temperature, is going to be 293 or 20 degrees centigrade, roughly. And of course, the other important temperature for liquid water going to vapor is 100 centigrade, which would be 373, right? And so these scales are important, and their juxtaposition is important because, for instance, when we look at the states of fluids and gases, oh, that's a horrible bracket, isn't it? That's a bit better. We write the ideal gas law as pressure is equal to density gas constant times temperature. Importantly, and you should never ever forget this, these are absolute pressures and absolute temperatures that we have to use. And if you don't use absolute pressures and absolute temperatures, you'll get ridiculous results. The other corollary of this is that we can also write this as equal to absolute pressure, density, and the universal gas constant divided by the molecular weight of whatever the gas is. I guess mass, isn't it? Molecular mass. Again, relative to absolute temperature. And so this is a universal gas constant, a single number for all gases, but divided through by the molecular mass of that particular gas. This is a different one. This is for the constant for gas, quote unquote, I. Nitrogen, CO2, air would be mainly nitrogen with some oxygen in it. And we also know, I guess, that since we know what density is, we could also write that as the mass of gas divided by its volume. Just rewriting that in a different way as basically the definition of density. And so those are the basic relationships that we might want to look at. We didn't look at a phase diagram, but perhaps it's useful to look at one. We said that we sit at 1 atmosphere or 1 bar. So if you like to think where we're sitting right here. And the temperature we're not at 0 degrees centigrade, we're not at 100 degrees centigrade, but we're somewhere in between. And so I imagine we're somewhere up here. And so not surprisingly, liquid water, if you have it in your flask or coffee as a doped form of liquid water, it exists at water this temperature. If we reduce the temperature, we freeze. If we increase the temperature, we boil as we go in this direction. But also, we can also vaporize it by, instead of being at this pressure, if we take it up to Everest, where the pressure will reduce, then maybe it will vaporize. Certainly, if you take it up even higher than Everest into the atmosphere, it will go from water to vapor. If we have frozen water at lower pressure, and all of a sudden we heat it from here, we sublimate. Instead of going from ice to water to gas, we go directly from solid to gas. Sublimation is the term that's used for that. And so these are component behaviors that we'll talk about. I guess the other thing that we might know is that if we look at this, water is not a good property to do this, but if you look at density, the density of water vapor is quite low. The density of water comparatively is high. And actually, surprisingly, the density of ice is lower than the density of liquid water, right? That's why ice floats. But maybe it's the unusual as a solid in that regard. The viscosities also are a little strange as well. So this viscosity is high, and this viscosity is low, and this viscosity is also high, super high, I guess, maybe 2 arrows. Okay. So those are the behaviors we have. What else? So the last thing I guess I was going to do today, but I'm not sure whether we logically get there, but maybe I'll quote the result and maybe we'll deal with it next time, is that we will use the ideal gas law. So the class is called fluid mechanics. So fluid includes liquids and gases, not really solids. And so when we look at compressibility of these and their behaviors, then gases are controlled in their compressibility by the gas law. Could be ideal or non-ideal. For our purposes, we'll just use the ideal gas law. And so it matters how we change the volumes of individual gases as to whether we do it isothermally, in which we take your bicycle pump, we put it in styrofoam, and we compress the gas in there. The heat that you generate gets contained within there, and then if the temperature, in this particular case, if you do it so that you blow away all the increase in heat by having a fast air go across it, then there is no change in temperature. And if there's no change in temperature, we can merely write this equation as in terms of the pressure and the density being constant if it's an isothermal compression. Starts off at 20 degrees, you compress it, you keep it at 20 degrees. If you encase the bicycle pump in styrofoam and do it isentropically, you keep all the entropy inside that container. So the temperature goes up, then no longer is this constant, and the relationship between the pressure and density is related by the ratios of the specific heats at constant pressure and constant volume. A number which is typically of the order of about 1.4 for air. And so the ideal gas law is something that we'll use to be able to define compressibility of gases. We'll use it next time to talk about the modulus of gases, because actually me communicating with you and maybe you communicating with me, the speed of sound depends on the modulus of compressibility, the bulk compressibility of gas in air. The natives are restless, I see. I hear. All right, so that's probably it for today. We will be back on Friday. I'm around today if you want to come at the end of class and chat. If you want to walk back to my office, that's great too. If there's anything else that you want to deal with, any questions,